Hello friends. Subject Electricity and Magnetism. Class FYBSC. Paper 2. Chapter 5. Magnetic Properties of Material.
Hysteresis and hysteresis curve. The magnetization in ferromagnetic material not only depends on magnetic intensity H, but also history of the specimen. For example, consider a ring made of ferromagnetic material and placed inside a toroid having n number of turns, n number of turns per unit length as shown in this figure. See here, this is simply the toroid and this is simply the material which is placed inside this toroid like this. This is the material. This is the ring which is a material. Okay. As current I0 passes through the toroid, this is the current I0 which is passes through this toroid. The magnetic intensity H is produced due to this current which is flowing through this, particularly we can say that toroid. The magnetic intensity H, that is vector H, is produced in. Hysteresis occurs in a system that involves magnetic field. Hysteresis is a common property of ferromagnetic substances. Generally, when the magnetization of a ferromagnetic material lags behind the magnetic field, this effect can be described as the hysteresis effect. This is very important. When the magnetization of ferromagnetic material lags behind the magnetic field, this effect can be described as a hysteresis effect. That means we can have this magnetization. That means vector M. Okay. And simply we can say that whatever the magnetic field is there, vector B. Okay. Now when vector M lags behind the magnetic field B, then it is described in terms of we can have what? Hysteresis effect. Definition. The meaning of hysteresis is lagging behind. Hysteresis is characterized as a lag of magnetic flux density. See here, magnetic flux density B behind the magnetic field strength H, like this. All ferromagnetic materials exhibit the phenomenon of hysteresis. To give you a better understanding of the concept, we will take an instant where a ferromagnetic substance is placed inside the current carrying coil, as we see previously. Okay, now this is simply the coil. This is a toroid, and the material is placed inside this toroid, or we can say that the ferromagnetic substance is placed ring shape like this. Okay, now this thing we have to keep in mind. Okay, where the ferromagnetic substance is placed inside this current, and what happens here, this current is flowing through this, particularly we can say that whatever the coil which is given here, due to the magnetic field that present, the substance get magnetized. Due to the magnetic field that is present, the substance get magnetized. If we reverse the direction of current, see here, reverse the direction of the current, then the substance get demagnetized. See here again. Okay. Now this current is flowing through this direction and which is flowing through this coil, and it comes out at this end. Okay. Due to the magnetic field that is present in this substance. Okay. See here. That is present, the substance get magnetized. If we reverse the direction, that means if we reverse the direction, see here. If we reverse the direction, that means exactly this current is now here and out here inside, and therefore what happens, this direction of current changes. In the first case, when current is along this side, then what happens, it get magnetized, and when we reverse the current, okay, then the substance get demagnetized, and this process is known as hysteresis. That means due to the change in direction of the current, we get demagnetization. Okay, initially it get magnetized, and if we reverse the current, then it get demagnetized, and this process is known as hysteresis. Okay, one can measure the total field B inside the ring using apparatus called Roland ring. This is a Roland ring. Okay, this is the apparatus where we have to uh, perform what experiment of this hysteresis. This is Roland. The intensity of magnetization can be obtained from, we already know this relation, obtained from this equation, M vector M magnetization. Vector M is equal to vector B divided by mu 0 minus vector H. And as we know, this magnetic field intensity is given by N into I, where N is the number of turns of the coil and I is the current flowing through the coil. In this figure, it is I0, but actually we write here N vector I. We can write like this. Okay. Now this thing we have to keep in mind. Then the magnetic field produced is, we know it, vector B0 is equal to mu 0 n into I. That means it is actually the vector H, and therefore vector H is equal to vector B0 divided by mu 0, where vector B0 is the field produced by toroid only. Field produced by toroid only. The ring gets magnetized and produces extra field due to the magnetization. This is due to toroid only. Okay, and the extra field due to the magnetization there, and therefore vector B is given by mu 0 into bracket. We already did this thing. Vector H plus vector M bracket complete. That means this is the total magnetic field, we can say. Okay, now this thing we have to keep in mind, and therefore vector M is equal to vector B divided by mu 0 minus vector H, which is equal to vector B divided by mu 0 minus N I, as we did previously. One can obtain this H for every M, every magnetization, for any current. That means if we change the value of the current, then what happens here? We can find this H for every M, for any current. Then hysteresis loop. The hysteresis loop shows the relationship between magnetic flux density and the magnetization field strength. The loop is generated by measuring the magnetic flux coming out from the ferromagnetic substance while changing the external magnetizing field. The relation between B and H in ferromagnetic materials is complex. It is often not linear and it depends on the ferromagnetic specimen as shown in figure. See here, in this figure, we see here that it is not linear and it depends on what type of material we use, ferromagnetic material we use for the experiment. That is very important again. Okay, and it is non-linear, therefore we can say that it is very complex actually. Okay, but how it is there, that way also shows. Now this figure, this total figure shows the behavior of a material as we take it through one cycle of magnetization. See here, this shows the behavior of the material as we take it through one cycle only, one cycle of magnetization, one cycle of magnetization. This is very important. Okay, one cycle. That means if we change the another cycle, then what happens? It may different. It may be a different graph or graphical representation. Okay, therefore this particular thing shows only what? Magnetization. Okay, of one cycle only one cycle. Okay, that means we can say that we can change this magnetic field. Okay, automatically what happens? The intensity changes, and how it changes, that is shown here. We have to uh, learn the details of this particular, what is saturation, retentivity, corrosivity, saturation in opposite direction in detail to get the thing.